give the talk here. All right, it started. So Alex, please take the stage.
Okay, thank you very much for inviting me. So today I'm going to be talking about magic angle, multi-layer moiré materials. In particular, I'm going to be arguing that there could be a BEC BCS transition in
Alex, I have an echo. I think you have a maybe
on. Maybe
you have two microphones on.
I have two microphones on.
Maybe.
I think it was just poor, slow internet connection.
Okay.
That is definitely possible. Is it better now, or do you still hear the echo?
It might be
echo.
Yeah.
Okay. If you wait a second, I can try to figure out these headphones.
Meanwhile, Andrea Young has cancelled. Did you note that, Rajiv?
Oh, I didn't know this.
I didn't know that.
His children have got COVID, so he's had to cancel at the last minute.
Oh, that's terrible.
Oh.
So
we have time to figure out the
the connections.
connection.
yes, there's no hurry. It
says there's only a single microphone, so okay.
I think it's good now, so you can restart.
Well, you've probably all had, well, maybe not. I closed it. So I'm going to be talking about magic angle multi-layer materials, and I'm going to try to argue that there could be this BEC BCS weak to strong pairing transition in twisted trilayer graphene. But before getting there, I'll just introduce twisted bilayer graphene because this is where that all started. So as its name implies, twisted bilayer graphene is constructed by taking two sheets of graphene and twisting them relative to one another. This breaks your microscopic translation symmetry, but does result in this much larger moiré superlattice that you see here, where the different regions of that lattice are distinguished by the local stacking. So here at the center, you have AA stacking with the carbon atoms right on top of one another. The superlattice is, again, hexagonal. Right, sorry. So back in 2018, Pablo Herrera-Ferrero's group at MIT constructed the system and found both superconductivity as well as correlated insulating behavior, provided the twist angle was chosen to lie close enough to what is termed the magic angle. And that's just plotting the resistance here from their paper, showing these superconducting domes with this intervening insulating state. So over the course of the past few years, an enormous amount of effort has gone into not only studying twisted bilayer graphene, but also into the synthesis of a number of companion systems. So far, there are 4 graphene moiré systems that realize the robust superconductivity that is seen in twisted bilayer graphene. Now, by construction, all of these 4 systems share many features, but they are nevertheless not interchangeable. And I'm going to, in particular, be focused on twisted trilayer graphene. So I'll start by, talking a bit about the band structure and how it relates to twisted bilayer graphene. I'll then move on to discussing some of the experimental observations in this system, focusing in particular on the superconducting pocket around nu equals -2. And then I'll, argue that this could be some BEC BCS transition. Before moving on, though, I should thank my collaborators. I've I've been working a lot with Jason Alicia, as well as postdoc Cyprian and Etienne. I've also been very fortunate to be working with Stefan's group. And in particular today, I'm going to be talking about work that was really spearheaded by Yunjin, as well as Yongchun. Okay, so like I said, to understand the correlation behavior of TTG, or twisted trilayer graphene, it's worthwhile to revisit what happens with TBG, twisted bilayer graphene, and why it displays such rich correlation phenomena. So assuming free electrons, one can calculate the band structure of twisted bilayer graphene by allowing interlayer tunneling to mix the low energy states of the two graphene sheets that you have on top of one another, which of course here correspond to the Dirac cones at the K and K prime points. Performing this calculation, you then find the rather remarkable result that around 1.1 degrees, the bands closest to charge neutrality become nearly completely flat. It's worth mentioning just at this point that this interlayer tunneling between the layers won't mix the two valleys, and so K prime remain good quantum numbers, and the resulting band structure is effectively fourfold degenerate with spin and valley flavors. And so we want to look at interactions. Well, we can roughly compute the Coulomb interaction scale, just the inverse of the moiré lattice constant. You find that it's, well, here I found it was 14 or 15 MeV, very rough. But that is most notably larger than the bandwidth of the system in this limit. And so the magic angle is just a band flatness condition, which of course makes it natural to speculate, makes it natural that the system may realize interesting correlated phases, which as I said, it does. And I'll get back to, of course. So of course, so now onto twisted trilayer graphene, which is what I actually want to be talking about. So the construction of this system is actually somewhat more subtle than what you had for twisted bilayer graphene. And you can think about it as follows. So you ensure that the top and bottom layers, so layers 1 and layers 3, are perfectly AA stacked on top of one another. The middle layer 2 here is then twisted by an angle theta relative to these top and bottom layers. Now, and this is what you need to have in order to get the physics I'm about to discuss. And this, of course, might seem a little bit insane because it's pretty impossible to ensure that these layer 1 and layer 3 are going to be AA aligned. However, fortunately, it turns out that lattice relaxation actually favors this type of alignment. So, provided you stack with the appropriate twist angles, the AA stacking should follow naturally. So when these conditions are met, the band structure of TTG, twisted trilayer graphene, can be obtained in an identical fashion to what I just described for twisted bilayer graphene. And what you find is that you can decompose these states that you get into two independent subsystems. There is one of those subsystems is identical to twisted bilayer graphene, but with a twist angle that has been that is smaller by a factor of 1 over square root of 2. And the other subsystem is simply a dispersive Dirac cone, identical to what you have in monolayer graphene, MLG. And so here I'm now just plotting those band structures side by side at their respective twist angles. Of course, the magic angle for twisted trilayer graphene is larger than the magic angle of twisted bilayer graphene by a factor of square root 2. But when you plug these in, you find that they look remarkably, similar, with, of course, the exception that you have this highly dispersive Dirac cone that is also, just hanging around in twisted trilayer graphene. Otherwise, however, so long as this cone isn't going to do so long as the cone doesn't do that much, it's highly dispersive, so you might expect it to be relatively inert. You would expect the physics of twisted trilayer graphene to also display interesting correlated behavior like twisted bilayer graphene. And so, and just to mention again, it's this fourfold degeneracy. Okay, so now on to the question of experiments. And so do all of the things I say happen? Is it as interesting? And of course, the answer is yes. So here I'm showing a figure out of a recent paper from Stefan's group that is plotting the resistance on the vertical axis against filling for different temperatures. So in this talk, I'm going to be measuring filling from charge neutrality, so it's nu equals 0, in the center of the figure. And here at this point, as expected, you find semi-metallic behavior, which is what you would get from your simple band structure. Moving to the right, corresponds to adding electrons. At nu equals 4, all of the bands are filled. However, the Fermi energy now still intersects this dispersive Dirac cone, and so it's a metallic state. And the analogous, happens for when the bands are fully empty at nu equals -2. So I've just described, pretty much the only characteristics that the band theory is going to predict for you from this phase diagram. Because as soon as the chemical potential has moved into actually the flat bands, various correlated phases arise. On the electron dip side, we have these 3 resistive peaks, as well as a superconducting dome around between nu equals 2 and 3. But I'm going to be mostly interested in the superconducting dome around nu equals -2. Since it is, it's larger and seemingly more robust. So spectroscopy.
Why there is so much asymmetry between?
Yeah, I was going to ask the same. Yeah.
I don't know. Yeah, that does definitely tend to be the case. These are different samples, of course. This is transport, and then this is just a trilayer graphene in STM. And again, you have the same very strong asymmetry. Yeah, I can't. Okay, I don't know who asked the question. Okay, moving on then. So actually, just point out, this is very similar, of course, to what you get with twisted bilayer graphene. Perhaps the asymmetry is more pronounced. But anyways, so here I'm showing what you get from STM. So STM measures DIDV, which is essentially the density of states. So that's what's shown in the colors. Vertical axis is the gate voltage, which is equivalent to changing the filling factor nu. So here, where my mouse is charge neutrality, fully filled, empty. And the bias voltage on the horizontal axis is measuring the energy as deviations from the energy from the Fermi energy. So you have this cascade physics, which, as I indicated, is related to these correlated peaks here. But what I really want to focus on is this extended suppression of the density of states around nu equals -2, which is of course exactly where that more robust superconducting dome showed up in transport. So we can zoom in on this region to see a bit what's happening. Well, first of all, up in this region here, you have these sort of jagged diamonds, and that's telling you that the system has a gap. So this is a correlated insulating state at nu equals -2. As you hold away from this, you then get this sort of persistent trench nearly up until nu equals -3. So there's very little in the way of density of states in this regime. And moreover, you have these telltale coherence peaks along the side, which is clear in this waterfall plot. So this is pretty consistent with what you would expect from an STM observation of superconducting gap. And you can also check that this behaves in the way you would expect under both increasing the temperature as well as varying and applying a magnetic field. An additional verification, you can do an additional verification by considering Andreev reflection. So essentially, the DIDV curves of SDM measure that I was showing previously, those are measuring the density of states. But when the tip is placed very close to the sample, it forms a normal superconducting junction. And so in addition to normal reflection, a superconducting state can also induce Andreev reflection. As shown schematically here in a figure actually from Ali Yazdani's group, they actually performed these measurements in the context of twisted bilayer graphene earlier. The upshot is that if you have a superconductor, you would expect a zero bias signal from this Andreev reflection. And that is exactly what is seen here. These dark peaks, to make sure that this is consistent, here is being plotted in red is the signal at zero bias. And then in black is the signal at 1 MeV. So you see that in the superconducting region, there's a definite enhancement of the signal, as a result of these Andreev reflection. Similarly, the Andreev reflection, of course, dies when you apply a magnetic field. Okay. So having now established that this regime here is in fact a superconductor throughout the entire throughout its entirety, the next step is to try to fit the conductance curves that you get with some theoretical expectations. In doing so, however, it quickly becomes clear that there are two distinct regions, which I will originally creatively name a U-shaped superconducting region and a V-shaped superconducting region. So the V-shaped region is actually closer to nu equals -3. So this would be perhaps an overdoped version of the superconductor. And it fits actually a nodal tunneling spectrum quite well. So this regime isn't really that mysterious ultimately. By contrast, what you could call the underdoped regime is the U-shaped regime. And here the line trace is much, differs, and that you have a very low curvature at the bottom. So you can try matching it to different fits. Here's a nodal fit in blue. It doesn't look very good. However, it turns out actually the S-wave fit doesn't actually work that well either. That could be a consequence of these of the large asymmetry, probably in the coherence peaks. But yeah, so if you want to get a handle on it, you can look at something even simpler than actually a fit, which is what is done here. Here you're just tracing the second derivative of the of the density of states. So that's the curvature at 0 bias. So that's just, you calculate a second derivative along this line here. And you can see that in this U-shaped regime, it's significantly smaller than what you get in the V-shaped regime. And I'm going to take this as an indicator that, as I would have guessed from how it looks, that you can in fact say that there are few states present at the Fermi energy in this regime. So this is some sort of gap state. Okay, so now I want to put forth an explanation for what I've just described. So one potential explanation is that you simply have a changing, that the superconducting order parameter is simply changing as a function of filling. So you could be, there's these asymmetries, so that's why this isn't fitting very well to the S-wave shape. It is nevertheless still some, gapped superconductor. And then as you dope further away from the correlated insulator, you wind up in this V-shaped regime. That's not the, there's another possibility, which is that instead what's happening is some sort of BEC to BCS or strong to weak pairing transition is happening as you sort of go between these two regimes. And I'll just emphasize before continuing that I'm not actually going to be saying anything about what the pairing means. BCS, as I'll say, refers to weak pairing in some more general sense. Okay, so the starting point for this scenario is that correlated insulating state up here. And so first thing I have to do is get a correlated insulator, because of course, if your chemical potential without symmetry breaking, you have 4 degenerate chemical potentials. This cascades and polarizes in some fashion. I'm going to very simply assume that these 2 pink bands are very high in energy, and then I'm left over with some blue bands that have opened a gap at the chemical potential. Now, how actually these flavors mix in the sort of final state is again something that I'll remain entirely agnostic to. But there are 2 flavors. So I now zoom in on these bands, and I'm going to start by asking what these regimes look like in this context. So the first regime is a BCS superconductor, and that is what you are usually dealing with because that's what is found in pretty much all systems. So here the chemical potential intersects this 2-fold degenerate bottom band. You can describe the fermionic excitations in the usual fashion by taking one of those flavors and re-expressing it as poles, flipping it about mu. Superconductivity then hybridizes the hole and electron branch, opening a gap, at least at charge neutrality, at least for some momenta. So the resulting state, is a condensate of very large Cooper pairs. They can be estimated actually roughly with the Fermi velocity divided by the pairing magnitude here. So now I want to go to the more exotic regime, which would be this BEC strong pairing regime. You could imagine getting there just by cranking up the pairing term, in which case the size of your Cooper pairs is going to get very small. And so the BEC regime is really what you get when your Cooper pairs are so small that they can be treated as charged to bosons on their own. The fermionic excitations at this point are more or less spectators. It's really, everything's really happening in some bosonic sector. So there's no need, of course, now for the chemical potential to be intersecting these fermionic bands I have here. Since we expect these Cooper pair molecules to really condense on their own. You can actually roughly interpret the difference in energy between mu and the top of this band as some sort of binding energy for the Cooper pair molecules. Nevertheless, even though the fermions are more or less spectators, as I said, you can still look at what you would expect from STM in this context. So that involves the usual procedure where you first re-express one flavor and then you add pairing. But of course, now because the chemical potential is lying in this gap, the difference is very minute. And so if I want to now go back to my to this experiment with trilayer graphene, I'll sort of switch back to the BCS superconductor. And in that case, as I said, we expect it to be a nodal, to have a nodal order parameter, so D wave effectively. And in this case, you have these Dirac cones. And so, the theoretical DIDV curve you would get is just a V shape with these conductance peaks. So that matches, as I've said, reasonably well, allowing me to identify the V-shaped regime with a BCS or weak pairing superconductor. By contrast, I now go to the strong pairing BEC regime and see that even though the pairing term does vary, as a function of momentum, it's pretty much invisible, from the dispersion's perspective. When you then look at the expected DIVP curve, you see that it has something U-shaped. In particular, there's no states close to the Fermi energy, which is offset here. Right now, probably somebody has noticed that they don't have this very striking coherence peak, and that is true. The argument I would give for that is simply that my model is not very good. There are a number of other states, high energy states, that are present. As I said, I threw away what I called the pink bands, but they could still be active in affecting the physics. So the main thing I want to emphasize is that I do have a low density of states, at the Fermi energy. That's sort of the key point. So I will identify this with the BEC phase. All right. So is there any other signature that what I am saying is anything more than just a story? Well, one thing is observation of pseudogap-like behavior in the BEC regime. So here, these are some traces in this U-shaped regime. It's a function of temperature. You can see that as temperature increases, the coherence peaks, die. So that's what's being plotted here in red. This is the coherence peak amplitude, and this is the temperature. So they're dead by around, I guess, 2 Kelvin. The suppression of the density of states, nevertheless, persists all the way up until nearly 7 Kelvin. That would be a T star. And so you can interpret, this extra gap as a manifestation of that binding energy for the bosons, which is, it gave you an extra energy scale, and that extra energy scale is what is setting T star. It's, up until T star, you still have these bosonic molecules around. Yeah. So moreover, and this is actually transport measurements also see indications that you could have this strong pairing behavior. So, and I should actually acknowledge that this was the sort of first, indicator that this BEC BCS story was present, although it was, of course, not couched in terms of a nodal order parameter. So this is a figure from the MIT group's data. The horizontal axis is filling with the correlated insulator right here. The purple line plots the TBKT, so the superconducting dome. And in pink, what's then being plotted is the Ginzburg-Landau coherence length. Now, in a BCS superconductor, the Ginzburg-Landau coherence length is really just the same as C pair, the size of those Cooper pairs. However, that's not the case in a BEC superconductor, where instead the Cooper pairs are now incredibly small, and the more important energy scale is the interparticle distance, which scales like 1 over the square root as a function of density, which is plotted on the horizontal axis. And not here is the deviation, and not here, sorry, is the filling of the correlated insulator at nu equals -2, because of course, it's really the active excitations need to be measured now relative to that insulator. And the data is pretty striking. It fits this 1 over square root of n curve really quite well. Whereas it has a very different behavior, on the other side of the superconducting dome, on the overdoped region. Okay, so hopefully I've convinced you that this story isn't completely insane, that there is like there are a number of experimental signatures pointing to the fact that this is at least close to some sort of BEC phase, strong pairing superconducting phase. But in the last few minutes, I very briefly want to sketch out a sort of important distinction between what I've just discussed and between the BEC BCS crossovers you normally hear about in the context of cold atoms. So in a cold atom systems, you have an S-wave pairing symmetry, and so your BCS and your BEC regime are both gapped. So this is they're ultimately just sort of different limits of a single phase. So this is a crossover. By contrast, this nodal transition I was proposing, the BCS phase is actually gapless, and so in order to get to this this gapped BEC phase, you have to undergo some sort of transition. This was first noted by Sade Mello and Batelho. And so you can ask what is going to happen at such a transition. So if you just look at the band structure, what you find is that there's a quadratic band touching. Here I've actually, quadratic band touching. So you could write down the simplest possible critical theory and try to see what happens. So that's what I've done here. I is just labeling those two flavors, as I said. This is this quadratic kinetic term. Mu equals 0 is how you tune towards the phase transition. Delta D is your superconducting order. And then, of course, for good measure, there is some sort of interaction term. Now, I've written this interaction as a density-density interaction, which I'm free to do so. However, it's more generic than that because there are only two flavors here, and this is a local interaction. So Pauli exclusion, pretty much limits what you can write down to a single 4 fermion term. Moreover, you can check just that in 2 dimensions, U is actually a marginal perturbation. So there's some hope perhaps that you can actually get universal properties out of such a theory. And I'm not, so this is sort of preliminary, but when U, as I've written in it, is positive, this of course, the theory becomes unstable, and actually in some narrow region close to the bottom of the band. So sorry if in some region, close to this critical point, you wind up actually with an instability to a D plus IS phase. So, so that's what I'm plotting here is this S wave order that's being generated. Here, the dashed blue line is where you would say the crossover now occurs because it's now at this S wave component. These 2 points here are, of course, phase transitions of their own right, because I'm now breaking some sort of time reversal symmetry. And if this is actually what's happening, one thing that you can check is what the excitation, fermionic excitation gap is, and it has this non-monotonic behavior. I will, acknowledge that this theory is missing one crucial component, which is, that this is the behavior of the bosons. But no, it at least tells you that if you say do not, in fact, reach a true BEC phase, it is still possible that you're, incredibly close to that transition. That is not really a wrong way to think about it. Okay, so in summary, I've hopefully at least shown that there are these 2 distinct regions. Regimes in STM in twisted trilayer graphene, and that they can be described by a nodal BEC-BCS transition, which is further supported by, the Ginzburg-Landau coherence length, as well as those Pseudogap measurements. So I, have a bit of the outlook here. So, what can this tell us about the microscopic pairing mechanism? Very little. I don't know that there's any. There was perhaps very little is known about these strong pairing superconductors in solid state systems. The next, so the next question is, what is the origin of these, Cooper molecules say? For instance, one of the theories for the origin of superconductivity in twisted bilayer graphene suggests that it's mediated by some skyrmions. And that would be, that type of excitation, would be one sort of candidate for these Cooper molecules. Twisted trilayer graphene also sees some sort of reentrant superconductivity. Is this related to that? And as I said, what is really that nature of that transition? So thank you very much. And
all right, thank you. Thank you for your nice presentation. So we have time for question already, and Andreev.
Alex, could you please show your Hamiltonian again? So help me please clear my confusion. So it looks like you're studying a negative U Hubbard model, right? Assuming your U is positive here, as written.
This isn't on a lattice.
well, still, it's a negative U as written. I mean, assuming your value U as defined as positive, then minus U density squared, shouldn't that give you? I guess what I'm trying to ask is that you seem to struggle.
I mean, the model is very simple. The difference is that you have this pairing term, and I'm holding this fixed across the transition.
Right, and then wait. So what were you changing? You changed the chemical potential to govern the transition.
Yeah.
I see. But that means, because what's written here, the second term is just the reduced BCS equation. So I fully expected to see another term that would look like delta D squared by modulus divided by U, right? And so that's my confusion. If you're already writing a reduced BCS equation, then you don't need the negative U term to mediate the pairing.
No.
Do right both, then you should have self-consistency condition.
Yeah. Well, so actually so I'm assuming that like whatever is giving rise to this delta D is very strong. So I don't need to self-generate it. If I were going to do so, however, you know, it's pretty clear that it will be irrelevant at the transition point. Because it has to have this, well, because it has this sort of kx squared minus ky squared behavior. So it actually goes like k to the 4.
Right. But again, just on general grounds, imagine you put this on a square lattice and say, look, I'm looking for cos kx minus cos ky d wave superconductivity in the cuprates, right?
Okay.
So would
you wouldn't get it.
What's written here is, you know, the reduced BCS equation. You say, okay, I'm postulating this delta D by hand. So then what is the last term? How should I think of it?
Okay, so I've said that the last term, sorry, maybe I should have emphasized that. I have no idea what the last term is. It is an interaction term that you can write down that is marginal. I was, you know, looking at what happens in the event that U is negative, but it doesn't, or well, that U is positive, I guess, in this nomenclature, but it could also be, you know, could take either sign. I don't know what it is. It's written as a density-density interaction, but that's just, it's just sort of convenience.
I see. Yeah, well, yeah, anyway, sorry, I don't want to dwell on this, but it would be nice to understand what the motivation was for writing it to be negative. I mean, if you wanted Hubbard U, you could just written, you know, U density squared, right? And as you said, using different channels, it would effectively give you a 4-channel sort of Hubbard model with spins and valleys.
So, okay, let's be, so what's happened? So this doesn't seem very stable, even if I ignore this thing, right? So you're asking, you know, just on symmetry grounds, what is there that could affect, you know, the stability of this critical point? And this is the marginal interaction that you would write down. You know, part of the motivation of looking at it was that there's something that looks like a first order transition here. And there's some physics that I don't fully understand. It's sort of something I was thinking about like this weekend that could potentially use this model to explain that jump, but I don't know that it really does. That's why.
Okay. Thanks.
All right. So Rajiv, you're muted, Rajiv.
I missed what the role was of the Dirac band. I mean, so you had these two split band, the twisted bilayer graphene type bands, and then you had a Dirac band. I mean, did the molecules come from that band somehow?
Oh, I completely ignored that band after a certain point.
Oh,
I probably
ignored. Okay, so I see. So molecules also come from these twisted bilayer. So why different than from twisted bilayer graphene? You said that this phenomenon is in this trilayer, right?
Yeah. So this isn't seen in twisted bilayer graphene. The Dirac cone actually, you know, from the sort of cartoon pictures I've given, it doesn't do much. But it does. So in this context, I don't really know what I would say the Dirac cone is doing. In other contexts, I think these extra bands that are present can reshuffle things in a way. That would be that quadrilayer and pentalayer case. But yeah, I don't have any good intuition for what that Dirac cone is doing. This is all, you know, phenomenological.
But it also loses its gapless states. Is that right? When you go into the superconductor?
Right. So something is happening with. So something is happening, at least in in this sample. Well, so okay. So one thing to note is that this sample from Stefan's group did actually find a correlated insulator in nu equals +2. So it is possible for the state to be opening like a proper gap. I don't think they saw such behavior around nu equals -2, but you could, you know, always argue that that's effective disorder, and that you know, whatever cascade physics you have that is giving rise, you know, to that correlated insulator I'm viewing as the parent state, that you know, induces a gap for your Dirac cone. Does that make sense, or at all address?
Maybe.
Yes.
Yeah.
Okay, great. Very interesting phenomenology. I wanted to know what the upper critical field looks like in this system, and whether there's any indication of Pauli limiting that would indicate maybe a singlet superconductor, or whether it perhaps is orbitally limited, which would give you rather different behavior in the two regimes. Do you know what the upper critical field looks like in the system?
Yeah, so this is from Pablo's data.
Okay.
This is they have a reentrant superconductor in what, you know, you could maybe interpret as the underdoped regime.
Mm-hmm.
And so yeah, I that would be one question, is, you know, I don't know how this type of scenario fits in to those observations.
But those are quite large fields, especially given what is TC for this system, or what is a gap size? I guess.
Well, okay, so that's the thing. I think if you take the BCS TC, this is Pauli violated. This does appear to be a super by about a factor of 3.
Mm.
It's significant if you take what you get in STM, that as the gap,
mm-hmm.
The separation from the coherence peaks, it is less convincing that this is a. Now it doesn't, of course, explain what this reentrant, you know, phase is, but.
But a 10 Tesla, well, it seems to go above 10 Tesla. Actually, it seems to go to maybe 12 Tesla at the upper critical field at around -2.4. So, but I don't know, but so I don't know the numbers, but it seems a very large upper critical field, and the reentrance is very interesting. Makes you wonder whether this is a triplet superconductor.
Well, that was so actually. This paper here is essentially is from MIT, and they're essentially saying what you're exactly that. So this is a triplet superconductor.
So if that's the case, can't you use the upper critical field as a guide to the coherence length?
Yeah, that's how they. that's how they calculated it here.
Oh, okay. So that's how they got that. Oh, I didn't
Yeah.
realize that. Okay, sorry.
Oh, I think. Well, no, I think these are a perpendicular field, of course. That's an in-plane field.
Sorry, the picture you just showed was a perpendicular field or an in-plane field?
That was an in-plane field.
Ah, so that's
Sorry,
just,
that's the interesting. I thought you're talking about triplets. So that's the one that.
But if it were in plane, then I see. Then okay, so if it were in plane, then you'd just be seeing the effect of the Pauli limiting, and the fact that you don't see very much effect makes you think that the spins might be parallel. It might be a triplet state with parallel spin pairing. Is that the idea?
That yeah. So the fact that the in plane, you can go to large fields that are larger than the Pauli limit as estimated from their transport experiments, was an indication that this could be a triplet superconductor.
I see. So
I don't think that is it's not nearly as convincing, because this isn't, you can't just take TC and assume that is the gap, right?
Right.
And then when you look at the gap, it isn't. It's.
Could you have alternatively then explained your transition as a reorganization of the D vectors of the pairing field if it were triplet, from a nodal triplet to a fully gapped triplet?
Yeah, that's the scenario I didn't like.
Oh, okay. Why didn't you like it?
So the reason so if you have a good reason for that to happen, obviously, it's just, you could just say, oh, it changes, and that's not entirely convincing without other information. Whereas this BC transition does, fit in with some of the other data. But, I'm not ruling this thing out.
It's 2D. It's 2D, so you could get nodal behavior in a 2D triplet system. I see. Okay. Very interesting. But I wanted to mention there is a in some of the 115 heavy fermion systems, as you dope them, they go from nodal to fully gapped. And that's been a system where we wondered it might be a Lifshitz transition, a kind of BCS transition.
Oh, interesting.
I don't know of any. Do you know of any other experimental situations where people have seen BEC BCS transitions?
There is a very recent paper in a compound that I'm totally forgetting. I'm wondering if it's some Kagome compound where they say that they're in the BEC limit. In that case, however, it is a S wave. It's a gapped order parameter, so it's not going to have this sort of transition here. I had never heard about this though in any other context. That was all I had actually known about. Since I've got you here, and people of course talked about it for cuprates a while ago.
Recently, Andreev Bernabig and collaborators have suggested a heavy fermion analogy for bilayer, crystal bilayer graphene. Would that also work for trilayer graphene, given that the Stritzer-McDonald model seems to be the same for the two?
So I'm not really familiar with that work at all, actually. But I mean, you would expect it to be, yes. That you would expect most things.
I guess there's the same, what do they call it, topological obstruction in the trilayer as there is in the bilayer. Is that the case? Okay, I see.
Yeah.
Well, maybe the connection with this heavy fermion system is not so crazy.
Interesting.
Okay. Anyway, thank you. Very interesting.